So I'm going to teach you about the Rubik's slide, which is a type of, it's similar to the Rubik's Cube, but there's a lot of differences to it. One of the main differences right from the start is it's not a three-dimensional object, it's only a two-dimensional object. And I'm doing my thesis on this. That's the object that you can purchase. It's available on Amazon, things like that. There was a paper, one of my thesis advisors, Dr. Thomas is one of them, but another thesis advisor had written a paper on the 3x3 and did a full analysis of it based off of the different levels of games. So my thesis is on the 4x4. When you extend it and make it larger, it becomes a much more interesting game, and it becomes a lot more challenging, actually. So this Michael Jones is one of my thesis advisors, and he wrote a paper on this. And there was also an additional set of mathematicians that wrote a paper called Rubik's on a Torus, which references the same concept. This is the 4x4 that we'll be looking at. And before we do that, we want to look at a toy version. Toy version is going to be a lot easier to work with. It's a 2x2 version, very small, and it's convenient for explaining some of these rules. And really, the general gist of the whole game is you're given an initial configuration where there's a couple colors, and then you're given an objective, which is your final configuration. And all you have to do is, how do I get this to there? Okay? And you only have 3 transformations that you really can do. So 6 total because it has inverses, but it's very simple. So the transformations you can do, you can move things to the right. So we can shift this to the right. We'll see how that affects it. You can shift something to the left, and you can shift it up and down, and then you can do clockwise turns. So on the 2x2 version, there's really only one type of clockwise turn. When you turn this, it's a 90-degree turn. But when we go to the 4x4 version, we'll see that it's a little bit different. So this defines the right shift. So if we take each square and color and then shift it to the right, notice how the green and the yellow go to the left, and then the blue and the red are now on the right. Okay, so what happens is when something falls off the screen, it automatically appears on the other side. Also observe in the 2x2 that left shift and right shift give you the same exact output. All right? Yes. So you can't just move one. Yeah, so everything shifts right. All the numbers will shift. Yeah, and definitely, if you have questions, ask because it only gets more confusing. The upshift and the downshift also happen to be exactly the same. We shift this up, the blue yellow goes up top. Shift it down, blue yellow still appears up top. And then the clockwise shift, you turn it to the right 90 degrees. That's the standard, so we're going with clockwise. And you'll see how the 4 interchange. And then counterclockwise is different because to get back to the very beginning, you would need to do 4 turns before that happens. Okay? So a counterclockwise shift is just to the left by 90 degrees. So let's look at an example gameplay on the toy version. So we're there and we want to get here. There's different ways that you can do that. One way would be if you do a clockwise turn, you end up with that piece. And then what could we do to get to here? Another clockwise, right? Exactly. This time, I think it's the same exact game, but we're going to look at it from a different perspective. This time, if we just shift it to the right, now at this point, to flip those, what could we do? Yeah, an upshift, right? And so then you get to that as well. So we're really concerned with, given any game, how many shifts do we have to do to get from the beginning to the end? It's one of the questions that was a concern of the Rubik's Cube itself. So that's really what we're going to be looking at. We're going to use permutation notation. You guys did that, right, in abstract algebra? All right, so we're going to use this heavily. Because what ends up happening is with all the colors or with all the numbers, it's really hard to keep track of everything, and it is the easiest way to do this. So how do we represent this? Instead of using 4 colors, we'll use 4 numbers, and just pick a standard. So the standard is top left is going to be 1, the next one's 2, and then this is 3 and 4. Sometimes some people pick 1, 2, 3, 4. We're going to use it this way. We shift everything to the right, and we see where the numbers go. And so then we can write this using permutation notation. So notice how 1 goes into the second position, so we have 1 goes to 2. And then 2 switches with 1, so 2 goes to 1, and then 3 and 4 the same. And for the 2x2, I actually don't use cycle notation because it's easy enough to write this out, and I think you don't lose it when you can see it like this. Your upshift is defined that way. So 1 goes to the 3rd position, 2 goes to the 4th position, 3 goes to the 1st, and 2 goes to the 4th. 4 goes to the 2nd. And then clockwise, 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. 4 goes to 3. All right, let's look at some composition. So now we can start to talk about, without even playing the game, I actually have us playing the game right here at the same time, but we can see that the math does the same exact movements. So normally, permutation notation, which direction do you do things from? You usually go from the right to the left, right? Yeah, right to the left, normally. Because we're playing a game and the way that we write these game movements out, we're going to actually refer to everything as from left to right. So when I say CR, normally in abstract algebra, you perform R first and then you perform C, whatever they're defined as. But here we're going to say, all right, we performed the clockwise movement and then we did a right shift on that. So we're going left to right. So we will read it from this direction to that. So we defined what C was, we defined what R was, and we just calculated. So 1 goes to 2, 2 goes to 1. Then 2 goes to 4, 4 goes to 3. So 2 goes to 3. 3 goes to 1, 1 goes to 2, and then 4 goes to 3, and 3 goes to 4. This tells us exactly what the object would be in if we were playing the game. And you can see it. 1 is still in its position, 4 is still in its original position, but 3 and 2 have swapped places. Okay? Imagine if this game was colored. If this was blue right here. What happens when you do a clock? So everything else is white, and this is just blue. You do a clockwise turn, and then a right shift, your blue ends up here still. Okay, so it would be blue and then all white. So this can represent all the colors at the same time, or can represent, sub games that we're going to have. We could also analyze. So we just saw CR, what that was, and that's an actual element of this group. We can perform a clockwise shift, and then a clockwise, and then a right shift, and then we get this position. So we can perform algebra on this, which is useful. The next part, and I think one of the toughest things, is you have to pick a naming configuration for all of your possible positions. So if you have all these 4 colors and you shift them around, every single place that they can go, you want to name that position. And we're going to use the letters to name it. We want to come up with a standard because there's lots of ways that we can refer to it. I found that the easiest way of referring to this was I will use C first, clockwise always first, and then reference the R's and U's later on. So here we saw that U was equal to 3412, okay, just the bottom. We also noticed that C squared R is actually equal to 3412 as well. So we can generate that element that we're calling U by just using clockwise shifts and right shifts. So we actually don't even need to know about the existence of U to name these elements. We can generate this group without the U transformation. All right? The U becomes useful later on because it's almost like a shortcut to get from one position to another. So this is the naming configuration that I'm using. We're going to use I as your initial configuration. So whereas 1, 2, 3, 4. A right shift is R. We can do a clockwise shift. We can do a clockwise right shift, clockwise squared R, clockwise cube, clockwise cubed R. That is all the possible positions for a 2x2 game. That's it. So there's only 8 possible places that you can move all these colors around to. Now, you could have come up with a different naming configuration. You could have put R's first, and it will affect what we have written there. Or you could have used U's as well, and it affects things. But this will be a nice logical way of working with them. All right. This just proves the hard way that these are the only elements possible. So if you start with I and do the 3 different places you can go to from I, okay, it writes them out, and then go from those 3, go and do all your transformations. You eventually exhaust all possible ways, and you see that there ends up only being 8, okay? I know when I first did it, I just didn't believe that there could only be 8. So I just did it out by hand to check. Okay, so the Rubik slide is an algebraic group. I'm going to, so I think, I know that you know what a group is, right? You guys know what a group is? I'm going to go through it anyway, just in case, at a pretty basic level. So these are the 4 requirements for a group. And I'm going to first use the integers as an example, just to show the integers are a group, right? So you need to have an identity element. So the integers with the addition, right? With addition as the process. 0 is your identity. The 0 plus anything is going to be whatever that anything was. It's associative. We know that there's the associative property of addition for integers. Every integer has an inverse. Positive integers have negative integers as their inverse. Negative integers have positive integers as an inverse. And if you add any integers together, positive or negative, you only get integers back out. So that's why that's a group, okay, under addition. So let's look at the Rubik slide as a group. This is our identity. And I go ahead and show it through an example. So with you, I composed of you, 1, 2, 3, 4. When you go ahead and do the math on that, you get 3, 4, 1, 2 back out. So you get you back out. When we do it from the other direction, so you do you first and then the identity, you also get you back out. So there's definitely an identity for this element, and you can test it for the other 8. It also has the associative property. So working left to right, okay, we can perform CR first. We saw it on the previous screen that this is CR. And so there's clockwise defined right there. So clockwise composed with CR, you get 3, 4, 1, 2. We could do C squared first then instead, if it's associative. And so this is C squared, and this is R. And so when you compose those two, you get the same back out. So it is associative. This is important, though. One of the things that always tricks me up here is, am I doing CR and then doing a clockwise shift on it? I'm not. I'm really taking clockwise and I'm applying CR to clockwise. Okay, so it's a little bit different. Here is an example of an inverse. The inverse of R is actually R. So because it's only 2 by 2, the second you shift it a second time, you're back at the identity element. Another inverse, the inverse for C is C cubed. All right, when you compose those, you'll get I back out. And an inverse for CR is CR is itself. In such a small group, there's not many options, so a lot of them tend to be themselves. And so here we can see that we get I back out as well. Right. And then obviously, this is a closed set, which is required for this to be a group. You do any of these movements, those are elements in our set, so it meets that requirement. So it is an algebraic group. It happens to be the dihedral group, okay, of 4, which is, you guys studied D4, I think, at some point. So all these groups mirror to something, right? They're going to be exactly the same. And this one is an 8-element group, and it fits perfectly with the dihedral group. And it's generated by R and C. So you do not need U to generate this set. All right, so this is where we're going to go off track of algebra, and we'll start to talk about graphing and things like that. I'm sure you probably did some type of Cayley graphs, okay? So these are 2 Cayley. You've seen Cayley graphs? No. Okay, so these are 2 Cayley graphs. They've got directed edges. So all the letters represent our vertices, okay, or the elements in our set. And then all the edges here represent our actual transformations that are available to us. So from the I element on the left one, we're only dealing with right and clockwise transformations. We can see how we can get to any position in that game. So if I wanted to get to C squared, there is no direct path from I to C squared using only right and clockwise transformations. I'd have to go, so we're using clockwise as the solid. I can go clockwise, and then I'm at C squared, okay? Or I could go, what's another way? I could go up, I could use, right transformation, and then I could do the inverse that direction. Let's go this way. I could go up here, I could do an inverse, I can go right shift to C, and then a clockwise and get to C squared. So there's lots of different ways that you can get there, but you see all the connections. If this is a game that we're playing, where does the up finally come in? Because we threw it away in the terms of generating our group. Well, up is our shortcuts. We can jump from places by adding this up position. So we can talk about this whole group with just right and clockwise, and a lot of things will remain the same, but we can get to places quicker with these up shifts. So from I've got an additional option. I can go to C squared R. So for me to get to C squared, now all I've got to do is an up shift and then a right shift. And then I'll be at C squared. Okay? And you can see it just adds additional vertices and edges. And the difference is, so your vertices don't change at all. Those are your elements. So you've got a group. R and C generate that group. R, U, and C also generate the same exact group, so they're going to have the same amount of elements inside there, which we're considering our vertices. But it's the amount of edges that we have, the amount of possible connections from point to point. Okay, so 12 edges when you don't use the upshift, and 16 edges when we do. Hamiltonian cycles. You probably didn't see this Hamiltonian cycles are really interesting things, especially because this pushes a lot of computer usage. Finding the Hamiltonian cycle of certain groups is a really big challenge right now. And there's no easy way of doing this except a very hard way by testing every single possible thing. So it exhausts even computers. Computers tend to help us out a lot, and we don't have an algorithm yet that is easy for us to use. So a Hamiltonian cycle is well, let me start with a Hamiltonian path. A Hamiltonian path is a path that takes us from one position and lets us go through every other element once, exactly once. So if I start at the initial configuration and I want to move through every single element only once, if I can do that, I found a Hamiltonian path. A Hamiltonian cycle is a path that actually ends back at your starting position, which is good. Because if we're playing, for example, if you're playing the Rubik's Cube, is there a set of movements that given any position, if someone hands you a Rubik's Cube, whatever configuration it's at, that you can perform those movements and you'll eventually get back to that same exact spot, no matter what way they give it to you? That will be a Hamiltonian cycle. And so with the slide, we're also concerned with that. Here's one that I think it might make more sense. Start at any configuration. Here I've defined the initial configuration to look like that. If I do a clockwise shift, and a clockwise shift, and then a right shift followed by 3 more clockwise shifts, I'm going to end at R. And then I do a right shift, and I'm back at I again. So you can follow those numbers, see how they turn, and I've gone through 8 elements, and where I started is exactly where I ended. That will work no matter what element I start at. So in this case, the Hamiltonian cycle is CCCR, CCCR. No matter what position I start at, if I perform those movements, I will always end up at the same position I started at. So I can beat this game guaranteed no matter what. It's going to take 8. It's going to go through every single element to beat it. Okay. Now let's prove that this is true. That's the fun. This is the well, I don't know if it's fun or not, but this is the good part of algebra is that we can actually see that this is really true. So I said that CCR, CCCR was a Hamiltonian cycle. So that's really C cubed R, C cubed R. Well, if you want to find out that C cubed R is its own inverse. So C cubed R composed with C cubed R gives you I. So it's guaranteed. We can also see this. So here's our Cayley graph. I go clockwise, 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 right shift. Clockwise, 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 right shift. The Cayley graph is really useful for finding it. Okay, this is 8 elements, so 8 elements are very easy to find. God's number. So it's such a nice name. It actually makes math sound like it's going to be really fun and powerful here. God's number, when we take it into graphing theory, it's the distance of a graph. Okay, so if God was playing this game, we assume that he's going to play it at the most optimal way possible. So if you give him a beginning configuration and a final configuration, he's going to get to that final configuration in the least amount of moves possible. So we want to know what that is for any possible game. If God was to play this, what's the least amount of moves that he would need? So using the Cayley graph on something small, it's actually easy to see. So what I do is I look at I, and I find a point that I'm definitely not connected to that seems to be really far away. And in this case, C squared is the farthest point from me. I'm connected to this guy, I'm connected to him. I'm not connected to C cubed R, so that's another point that is disjoint for me and could be a contender. But C squared happens to be one of the further ones. So how many moves does it take for me to get there? 2, right? And if you can compare this for anyone that I'm not a neighbor to. So if I'm not connected to you, then I'm not a neighbor with you. And every single one of them, it's only 2. Look at C cubed R, right? It doesn't matter whether we're using inverses or not. So C cubed R, I can go right here and there. There's 2. And there should only be one other one. CR, that's it, right? So 1, 2, right? So God's number for this game is just 2. It's nice and easy. But we're going to see that you can use the Cayley graph, but as your group grows, it doesn't become that beneficial. We can use graph properties. So these are definitely things that you have not seen. This is a strongly 4 regular graph. So first of all, for it to be a 4 regular graph, what that means is that if I'm at any element and I'm just looking, like I'm that element and I'm looking out, I see it looks exactly the same to me as if I'm C squared and I'm looking out, I see 4 paths. If I'm on C cubed R, I'm looking out and I see 4 paths. I can't tell where I am. It looks all exactly the same. And that's what makes something regular. And it's 4 regular because from every single one of these elements, there's 4 paths. Okay? So they've got to have that. Strongly gives this a really powerful conjecture later on. And the strongly piece is that every two adjacent vertices share the same number of common vertices, and every two non-adjacent vertices share the same amount of common vertices. And we can check this if this is true. So I and R, they're adjacent. The only vertice that they actually share in common is this one right here. C and CR, they're adjacent. The only one that they share is right there for a total of 1. So both of those have 1. C squared and C squared R, they only share 1 in common. C squared and R, they only share 1 connection in common. So it meets the first criteria. The second was, if you're not adjacent to each other, then you also share the same amount. It doesn't have to be the same amount as this, but they've got to be the same amount together. So C cubed and C squared R are not adjacent vertices, right? They're not neighbors, they're not connected. Now, what ones do I share in common with these two? Let's see. Every two non-adjacent vertices share the same amount of common. You see it? All right, good. As long as you see it. All right, so here's a nice little theorem. Every strongly regular graph that has two non-adjacent vertices that share at least one common vertex have a distance of 2. So this has been proven across the board. If you can find a strongly regular graph, by default, they definitely have only a distance of 2. So those instances actually they're not interesting because they're too easy. This is another way. We have a thing called a bipartite graph. These are two disjoint sets, which means this set right here contains all vertexes, all vertices that do not share anything, they're not neighbors. So I, CR, C squared, and C cubed R, they're not neighbors. These 4 are not neighbors as well. And so if we can create two disjoint sets like this, then we can make this bipartite graph. Interestingly enough, look that each one of these, they all have 4 connections. I connects to these 4, CR connects to these 4, C squared connects to these 4, and C cubed R connects to these 4. I think this is the easiest way to see God's number, because the furthest point from me are these 3 right here. If I'm I, the farthest elements to me are the ones that are in the same set with me, because we're all disjoint. And for me to get to any one of those, I just need to go to any of these elements, and that's 1 skip, and then you're over to there. So there's 2. I mention this because I think for the hard problem that I'm still working on, this is going to provide some insight that I have not found yet. But I'm really banking on this concept to help me solve that problem. And then finally, the adjacency matrix. This is linear algebra. So there's a wide range of stuff here. So an adjacency matrix, and I'm pretty sure you haven't seen this because I didn't see this yet until I taught it myself. Each row and column will represent one of the elements in the group. So for this 2 by 2, what that means is we're going to have 8 rows and 8 columns since there's 8 elements. And you're going to put, when you're looking at the columns, if I'm element I, I'm going to put a 1 for every neighbor that I've got. I only have 4 neighbors, right, because I've got 4 connections. And then all the other elements are going to be zeros. And so I'm going to fill that out. And so here are the 8 elements, right? And so, for example, I and R, they're neighbors. So I'm going to put a 1 there. I and C, I'm going to put a 1 there. But I and CR, I'm going to put a 0 because it's not a neighbor of mine. So when we fill this out, get an adjacency matrix. This represents whether an edge exists between you and the other element that we're comparing it to. Interesting property is that we can look at the polynomial of this function. So notice if we go back real quick, along the diagonal, you have all zeros. This really represents if you were to do one movement, you connect it to your neighbor, so you put a 1 there. And that's really a to the first power. So if we're calling this matrix A, the 1, a to the first power, represents we've done 1 transformation, and these are my neighbors. What if I did 0 transformations? I mean, I'm myself at A0, right? So I should have a diagonal of all 1s, and that's our identity matrix. So let's take a look. A lot of explaining here. Okay. So a 0 walk, a to the 0 power is your identity matrix, a matrix of all zeros except along the diagonal, you've got 1. And then a 1 walk is your initial identity matrix plus the A matrix. When you add those 2 together, we see that we still have zeros. Our goal is to find a matrix that has no more zeros in it. If we find a matrix that has no zeros in it, then what we've contacted every single piece, every single transformation inside. And so if we do a second walk, I plus A squared, all right, we end up finding a matrix that has no more zeros in it, right there. So here's I plus A squared. It's a matrix that has no zeros. Interestingly enough, the degree of that polynomial is your God's number, and that will always be the case. So we can use a lot of computer programming to make some really large matrices and compute this stuff pretty quickly. Okay, that's for this. It's small. We've seen God's number over and over again, but for some of the larger sets, this is going to be the easiest way to do this. Okay, the 4x4 easy version. So now we're going to really see how things can change. There's an easy, a medium, and a hard version in the game that you can purchase. All right, the easy version is just single color 90-degree shifts. The medium version is 90-degree shifts with 2 colors. The hard version is 30-degree shifts. Okay, and a 30-degree shift is when I go right, the number that was there is now here. The number that was here is now there. Okay, it takes you 12 shifts to get all the way around back to I on the hard version. We're going to only look at the easy version today. The easy version with that 90-degree shift, and we're going to consider all 16 colors so that we can just analyze the full game. Here, you're going to go through the same stuff, the initial configuration, final configuration. How do we get from one place to another? Right shift, if we define 1 through 4, and then, do with that counting. A right shift, notice how that column of 4, 8, 12, 16 is now here. Everything else shifted to the right. And then a left shift is no longer the same thing as a right shift. So on the 2x2, it was too small. Left and right were exactly the same thing. This time, a left shift or right inverse, okay, gives you a different result. It does. You shift everything to the left, and then your 1, 5, 9, 13 end up here, and then these 3 are over. Same thing with the upshift. Up and down now truly exist. They're not the same exact elements. Okay. And your clockwise shift still takes 4 turns around to get back to I on the easy version. And so you just have a lot more numbers that are shifting around. Example game, we've got this, and when we're trying to get to this final configuration right here, one option would be to do a clockwise turn. Do a clockwise shift. Notice how this element goes to here, and that top element goes over to here. What do we need to do to get to the final? Down, right? So U inverse is down. And we can also look at it that way. We could have went left. Right inverse is left. And left would give me this. And then I could have gone up 3 times. If I go up 3 times, 1, 2, 3, and then this is 1, 2, 3. And so you can end there as well. Game 2, this time with 2 colors. We want to get over to here. So we can do a clockwise shift, and it brings it over to there. And then what do I got to do to get there? Right shift. Exactly. One right shift, and you end up with there. Here we could have also done an upshift. So an upshift moves it like that, and then a clockwise shift. Clockwise shift will, from there, we'll move those 2 pieces in this direction, and then that one over there. All right. Now, if we were to write permutation like this, it's going to be a really long thing. So now we really need to use cycle notation. You guys saw the cycle notation? Good. All right. So cycle notation, though it sometimes seems a little bit more confusing to work with, it's going to be our friend here instead of ever writing it out like that again. Okay. And you can see, using cycle notation, that there are these cycles that naturally appear in the right. Okay, so they're in groups of 4. And so that defines what our R is going to be. And this defines U, and that defines our C's. We can perform the same permutation composition on them. So C and R, because there's so many numbers, I color them for us. We've got this is the definition of C, this is the definition of R. And so you can go from 1 to 4, and then go down to the purple, which is 4 to 1. Notice we don't write the 1, right? So when you go to yourself, we leave that out in cycle notation. And so we end up with this set right here. This is really convenient. If you really understand what's going on, you can read this and draw the board. All right. This tells me when if I'm writing out it as a numbered board, what this tells me is that 1 stays in its same exact position. It never moves. It tells me that 2 from the initial configuration is now in position 5, right down there. This tells me that number 5 is now in position 4, which is over there, and number 4 is in position 13, which is down there. Okay? And then 3 and 9, when you only see 2, that means 3 and 9 swap. They swap places. And so notice that here's 3 in the 9th position and 9 in the 3rd position. And you can do that for all of those. I put a colored game over it so that you can actually see. And this truly does represent what's happening. We're talking about all 16 colors here, but it does cover the movements of just those 2 colors with the 4 boxes. Questions? All right. So the naming configuration for this. There is no, or at least I'm not aware of, a nice, easy way to figure this out. This comes from a lot of experimenting with the elements and seeing what is out there. This one really names very well. And if I go ahead and define that all of my elements are going to be going with the C, and then the next one's going to be an R, and then the following movement will always be an up. That's the convention that I'm going to use. I can exhaust 0 through 3 for all of those, and it's going to cover every single element that actually exists. So for example, U to the 3rd is really C to the 0, R to the 0, U to the 3rd. Okay? CR squared is really C to the 1st, R squared, U to the 0 power. I is all to the 0 powers, right? Because you're not doing movements when you're at a 0 power. And then C squared R U cubed is C squared R to the 1st U cubed. But we can let those numbers run from 0 through 3, every single possibility that you have, and that's going to cover all of the elements. There are 64 elements in this group, all right? So we went from only having 8 in the 2x2 to having 64 in the easy 4x4. Here, this just shows that it is an algebraic group again. So I is defined as that in cycle notation, and when you do I composed of R, you get R, and R composed of I, you get R. We also see that it is still associative. Okay? So it's just using cycle notation to calculate these. And this is the inverse. Inverse is a little bit more trickier to find. You can look at some of the elements to come up with that, or you can almost write, what I sometimes do is I write this out, just the red, and then I say to myself, okay, I need 1 to get back to itself. 1 goes to 15, so in this other element that I have, I need 15 going to 1. So here's a case where 15 goes to 1. But see, I've got more elements inside here, so 15 goes to 9, so I need 9 to go to 15, and so I can write that out. And then 9 goes to 7, so in my inverse, I need 7 to go to 9. And then finally, 7 goes to 1, so I need 1 to go to 7. And so I can work it backwards to get that. It's a lot of head games on that, but you can do that. And you do that for all of this, and you find out that the inverse of R squared U is R squared U cubed. And it's important that we're writing this with the R's first and then the U's second, because that's the naming convention I use. Here's another example of an inverse. C squared R cubed U cubed is actually its own inverse in this case. And then the set is closed. Okay, group ID. This group is generated by CRU, okay? And this is actually the name of the group, okay? It's a complicated group, but that is the name of it. I use GAP. I'm sure you haven't. There's a nice computer algebra program called GAP. GAP software, and it's totally free, gapsystem.org. Very powerful for doing abstract algebra, and you can define some transformations, and it can tries to identify the group ID as best as possible. But that's this one, and does a lot of other powerful stuff. All right, let's look at the cosets. This group really works out nice. I wish the hard one actually worked out like this too. It doesn't, unfortunately. So we have a subgroup H. So we've got this big group that's got 64 elements. There's actually a nice little subgroup inside there. And that subgroup is a group that's generated just by right and up shifts. So we get rid of the clockwise shift altogether and just do the right and up shifts starting at I. We get a really nice group right here. And so the dashed ones here are your ups. So ups are all those. And then the rights are to the right. If I'm at I and I go right, I end up here. And if I go right again, I end up right squared, and I go right one more time, I'm at right cubed. Right at one more, and I'm back at I. And if I go up, I'm there. If I go up and then right, I'm actually at RU, and then right again, R squared U, and so forth. And this is a subgroup, okay? Now subgroups you have your left cosets to your subgroups. So if we take C and apply it to this subgroup, we can get all the left cosets that exist with it. It works out that you can think of this game as a 4-layer like parking deck, and this is layer 1. All right, this subgroup is layer 1. The 3 other cosets build up on top of it. So the group is non-Albanian. It's not commutative, the full group, but this subgroup is. All right, and that's something to really keep in mind because it's important here. It's not normally you can't do, for example, you can't do a clockwise shift and then an upshift and assume that an upshift and a clockwise shift will give you the same object. It's not going to. But when we're only talking about right shifts and upshifts, they give you the same exact object, so it's completely commutative. Now, to get from this subgroup to its next coset, so the cosets are going to be H, C squared H, and C cubed H. We can start at I. Now, if I go C, if I do a C transformation on I end up at C, okay? It's a whole other parking level. It looks exactly like this. See, it looks exactly like that. Except now I've got CR, CR squared, CR cubed, and I've got it for all of these. That was from I going to C. Important to note, if I go from R and then I do a clockwise shift on that, that is not taking me to CR. So don't assume that. I used to assume that because it's not right. Okay? Because it is non-commutative. So CR and RC are not the same exact element. It will take you to another element inside this coset, but it's not taking you to that one. Okay? I believe it takes you to CU. And then this is the this is the second coset, C squared H. So this is layer 3. And here we have all C squared. And then finally, we've got C cubed H. And so those are all 64 elements. It is a really nice structured object. Very nice. And we can see that we can travel through each of these cosets in the subgroup by doing clockwise transformations on I. You can from the others, but it's not going to just go straight up. Like if you're thinking of this as layer on top of layer, you're going to bounce around all over the place. Okay, and that's observer you see and see you or not. Okay. Now, we can talk about how many edges there are. So there's 64 elements. Every single one of these elements have 3 forward moving. So if we throw away the inverses, they each go forward 3 spaces, 3 locations. They can go there, here, or the clockwise shift that takes you to another level. So that's 3 of them. Times your 64 elements, there's 192 edges. So we're not going to draw this out. The Cayley graph had, 12 edges or 16 edges. That's easy to draw. This isn't going to be easy to draw as one object. Okay. The Hamiltonian cycle. I worked this one out by hand. Having this nice image, I was able to actually find one. And so it's this word right here. CRRRURRRURR. Okay, that all to the 4th power. If you do that many times, you will go through every single element, and it's actually really easy to see. So if we start at I, my first move says go clockwise. So I leave here, and I'm now here. Okay, I'm gonna leave the subgroup for last word. Now I'm here, and I'm gonna go 3 rights in a row. So 1, 2, 3, and now I'm gonna go up, and now I'm gonna go 1, 2, 3 in right shifts. And then up, 1, 2, 3, and then up, 1, 2, 3. So now I'm at CU cubed. At this point, I need to do clockwise. I just got to figure out where does clockwise actually take me. So when I go clockwise on that, clockwise on CU3 brings me to C squared R3. So C squared R3. This is where it takes me to. Right? So you do your permutation, composition to figure that out. And now I'm here. And now I got to start that process again. So I went clockwise. Now I go right. So R, up, R, up, sing 1, 2, 3, up, 1, 2, 3, and I end here. I go clockwise on this. So when I was doing this, my goal was I just need to, each coset, let me just get through every element and then move on to the next board. And then when I get to the very last one, which is our subgroup, then I'll worry about really how do I get from one place to the next. So when I go from here, C2, R3U3 goes to C3, R3U. C3, R3U. This is where I end up. So I do my 3 right shifts, I go up, I do my 3 right shifts, I go up, and then my 3 right shifts, and I go up, because I haven't finished these guys yet. and then I do my 3 right shifts. 1, 2, 3. And I started there. So I've exhausted all of those elements. And now I've got to go clockwise on this. Go clockwise on that, and it takes me to, now the third set. So it takes me to end at C3R3, C3R3U. C3R3U ends at C3R3, and that takes me to U here. All right. So I'm in the subgroup now. I started at I. I want to end here. So I have to look into. I mean, it would be great if it worked out perfectly, and it did. So what do I do from here? I go right 3 times, up, right 3 times, up, right 3 times, up. Brings me to R, and I go right 3 more times, and I end at I. So there's your Hamiltonian cycle. You can see with 64 elements, it's not. You have to really understand that structure of your object to be able to find this.
So with the hard version, can you way more elements?
It's like 2 billion. No joke. I'm still trying to figure out why. 2 billion. Yeah. So we go from 64 to 2 billion. It's insane. I wish it wasn't the case. All right, so here's a proof that this is a Hamiltonian cycle. So we can group these together and get all of those. And remember, the subgroup, the U's and the R's are actually commutative. So I can flip these guys all around, and I get R12, U to the 3rd power. R to the 12th power, if you do that 12 times, R goes away. It's at I. So this is really CU to the 3rd to the 4th power, and that's equal to I. You got to trust me on that. One of the assignments, if you're interested in doing that problem, is to show that CU cubed to the 4th power is equal to I. All right, God's number. So this is really easy. We've got a really good structure for this set now. So this is not that hard to figure out. If I'm looking just at the subgroup itself, I want to say to myself, what's the farthest point in this subgroup if I'm I? What do you think the farthest point is? Actually, it's not R3U3. It's not. Because R3U3, I can get there by just, I can do 2 clockwise, I can go, sorry, not clockwise shift. I can go this way, I can go left, and then down, and I'm there. R2U2, that's the furthest one. No matter what I do, and a lot of different ways to get there. It's 1, 2, 3, 4, it's 4 steps away, okay? So however I want, R2U2 is going to be the furthest vertex from I. That's 4. Now, every single board, every level is built the same exact way. So every level, that's the furthest point. So now for me to get to any point, any of those boards, think of it as the 4 in a row, right? If I'm at the bottom, to get to CH, I just move up 1. And then the furthest point is 4 away, right, from there. So that was 1 plus 4 is 5 moves to get to anywhere on CH. I could go down, and I'm at C3H. So if I'm at I, and I go down to the lower coset, I'm at C3H. Again, that's 5 away, right? So the farthest coset is C squared H, right? And that's only 2 away, so 6. So that's your God's number, 6 for this, just using this concept. So nice logic to figure that one out, especially if you have a nice picture to go around with it. So here it is. Yeah, so that explains all of that right there. So C2H is the furthest coset. It's 2 transformations away. On every level, you're only 4 steps away from the farthest point. And so a total of 6. We can use the adjacency matrix on this too, and that's really useful as well. I was going to post it in here, and then I realized my numbers were all wrong in it. I don't know why they were, but they are. But we can go ahead and do that. 64 rows, 64 columns. It's hard to do that by hand, but it's not bad if you have MATLAB or Maple to do 64 by 64. Not bad at all. And so you can place that in there, and you will see that the degree of the polynomial is 6. That will give you that first set. Okay. Yeah, and here I have you do it. This is how you would do it by hand. You actually want to make the adjacency matrix by hand because you really get to know your element that way. Start at I, calculate all 6 vertices, all 6 neighbors that it has, write them down, go to the next element, okay, and write those all down. You want to end up labeling each of the rows and columns by number, and then just have an index and say, okay, I is element 1, R is element 2, and things like that. So then when you're working with your matrix, you can just reference the numbers. Now, the subgames. This is where it gets really interesting because it's almost like, well, that's pretty easy. We found out God's number. Is there anything else to study about this? The subgames provide you a whole bunch of structure. So a subgame has less elements than the group usually. It could have at most the same, but a lot of times it's going to have less. And a subgame is sometimes when it's just a couple colors. So here's a subgame. I'm going to say that this is my eye. I've got that block colored and that block colored. So 1 and 11. That's position 1 and 11. And there's only a certain amount of elements I can get to by doing clockwise, right, and up transformations on this. And these are all the possible games. So if you were playing the game and someone gave you this, there's only 8 possible answers that they could give you. Like they could never give you, okay, that's blue and that's blue. It's impossible to reach. So we can go ahead and make a Cayley graph for that. And when we see there's 8 elements, this is the same thing as the toy version. It's the same exact group. It's the dihedral group 4. And this has a graph distance of 2. Also notice there is no clockwise turns in here. Because the clockwise turn, if I turn that clockwise, that's blue and that's blue. Well, that's just R3. So I don't even need clockwise turns in here to talk about this. So with this in mind, some things to think about. So why are there less elements in this original group? Okay, I mean the one thing is these numbers overlap each other. I mean they're the same color. All right, that changes things. What if this was 2 colors? If this was blue and this was red, this Cayley graph no longer works. We get more elements. Things change. So we end up getting, there's a lot of interesting objects in here, and I've highlighted a bunch of them here. These are all the possible 1, 2, and 3 colored games with single colors. All right, so then go ahead and mix and match it with different colors. There's a lot of different games to analyze. So when it's just 1 color, we've got an order of 16. So there's 16 possible games 16 possible final configurations we can go to, and it's got a God's number of 4. When I color these first 2, there are 32 possible elements in this game, and that's got a God's number of 4. Let's look at some other. Here's a big one. You color these 3. There are 64 possible places that can end up, and that game with an order of 64 has a God's number of 6. Okay. Nothing's going to be greater than 64. Notice that all the 64s do have a God's number of 6. All the 32s do not all have a God's number of 6. This 32, so these little ones that stand out, that one right there, it's got 32, an order of 32, and it's got a God's number of 5. That stands out because all the other ones have 4. So it's interesting to think about why is that the case. Here's a odd God's number. That stands out to me because all the other ones are even. So this one right here, those 2 lit up, 16 elements, and a God's number of 3, which is odd for this case. All right. But where does it start to lose like, we can go all the way up to coloring all 8 of these. Once we color over 8 of them, if I say, like, well, what about the game that's got 9 blues? Why is that useless to us? Think about why that would be useless. Well, not even that it covers the whole board. It's really, we've already talked about it. If we color 9 of these, then we're really talking about the one when it's colored with 7. Right? It's the white ones are then acting like the blue. So you only have to analyze all the way up to 8 of them being colored in. Now, the one that's 8 is really small and simple. There's only a couple places it can be. That's that. But this will all be always smaller than 6 or less, because God's number for the 16 colored board is 6. So it's definitely going to be less than that. It will have at most 64 elements. It's not going to ever have more than the 16 colored one. And then get all these other interesting group structures out of it. And then the final thought on this is, when we change that damn C to just C to the 12th, so instead of doing 90-degree shifts and we just do that 30-degree shift, this drastically changes it to 2 billion plus elements. I mean, it's insane. I actually created an adjacency matrix of 2 billion elements, so it's 2 billion columns versus 2 billion rows. And it was 120 gigabytes of data. So you can't open up a file that is that large. So I ended up breaking it into, it was like, I don't know, a couple hundred megabytes each file, and would only have a section of that matrix. And when I went to compute it, I tried to run it on it. It was going to take years. So there has to be some other way of, going to find some relationship, something going on with that, because we should be able to answer that. They answered it for the Rubik's Cube. It's pretty big. Rubik's Cube is bigger. And Rubik's Cube took like 20-something years to answer it, you know? But if we can find that structure, because I need to find it kind of like by December, we'll have an answer to what that is. I mean, I think it's under 20. Rubik's Cube, I think, is 21 or something like that. It's somewhere around there. I think this is less. So I think it's, you know, less than 20. But I could be totally wrong. Could be 40.
Then you say you wanted to draw in that type of disjoint.
Yeah, I really would like to do that because I think if I can get a whole bunch of disjoint sets, then it's just like island hopping, you know?
Yeah, you can try to figure out
Exactly. But it's 2 billion elements to kind of figure out where they place. It's a well-structured, in my mind, I don't think this is a mathematical definition or word. To me, it's a well-structured object. There's really good structure to it. It is I believe it's a regular object as well, that it's 6 regular. So it's got to have some properties, but it's just so many elements and too many assumptions to check and calculate. But that's for another time. Hopefully I'll have it soon. So I have exercises for you. I don't know what time. I'd encourage you to start working on it now because I'm here and I can answer questions. It really seems easy when you see it on the board. And the second you go to work on it, you get a lot of questions that pop up. And this presentation is online. That's the other nice thing. So write this down so that you can get access to it. I have a website. It's listed on there. I'm going to also put this video up there as well.